Okay, the next few segments we're going to be looking at some classic problems of synchronization and solutions to them. So, synchronization, as we've been looking at for quite a while now, is when you have multiple processes which deal with the same resources or memory locations, and there is potential for a clash between them for your, say, your data to get corrupted or different kinds of problems. There can be a deadlock, as we just saw. There can be what we called the bounded buffer problem, readers writers problem. There are multiple things which can go wrong when more than one process is trying to work with the same entity. Ultimately, that is what it boils down to. And synchronization is about how you try to effectively let these processes run in parallel as much as possible without any mishap happening, right? So we're going to be looking at some problems. We'll look at bounded buffer, we'll look at readers writer. We already saw the critical section problem. We'll be looking at something called the dining philosopher problem. So we start with a very simple thing, which is the bounded buffer problem. So the idea of the bounded buffer problem is you have a buffer which is like an array. You have two processes to keep life simple, the producer process and the consumer process. So true to their names, the producer process is going to keep producing pieces of information. It's going to keep writing something onto your array, your buffer, and the consumer process is going to consume that information. It's going to read that information from the array. So we can interpret this as the producer producing full buffers for the consumer and the consumer producing empty buffers for the producer. Ultimately, that is what it is. The producer keeps writing onto this array, the consumer keeps reading from that array. So every time the producer puts something inside, the consumer is going to take that. That's the idea. That is what is happening. So how is it happening and what is the problem? So before we go into the how, the problem is your array has a fixed size. Okay, we're dealing here with fixed sized arrays, not dynamic arrays. So if your array size is 5, the producer can put at most 5 elements onto the array. The consumer has to consume at least one of them before the producer can put the 6th element. Meaning, the producer must not try to produce information when the buffer is full, right? Secondly, there has to be at least one piece of information on the array for the consumer to be able to consume it. The consumer must not try to consume information from an empty array. So for those of you who have done data structures, if you've done stack and queue, there is this idea that you cannot pop from an empty stack, you cannot push into a full stack, right? Same with queue. That's the exact idea I'm talking about here. If your buffer is full, your producer should not produce information at that point, because it cannot put it in the buffer, the information is lost. Similarly, if your buffer is empty, consumer should not try to read at that point, because there's nothing to read. It is wasting time, energy, clock cycles, resources. So how do you tell the producer when it is allowed to produce, when it should not produce? And how do you tell the consumer when it can read, when it can consume, and when it should not? This is the bounded buffer problem. This is how the problem is defined. So what are the solutions? There, of course, for any problem in computer science, it is highly likely that you will have multiple solutions. We will look at one solution here, which is based on semaphores, because that's something we just looked at and we are familiar with. So we have the producer process, we have the consumer process. We will look at each of them. Before that, because we want to avoid this clash pertaining to our buffer. So when the buffer is empty, consumer should not read. When the buffer is full, producer should not write. To enforce these constraints, we take the help of some variables, integer n, which is the size of my buffer, and 3 semaphores. The first semaphore is called mutex, initialized to 1. This is a binary semaphore. So when the name says mutex, please don't get confused. Is this a semaphore or is this a mutex lock? Technically it is both, because when I was explaining semaphores, I said binary semaphore and mutex lock are the same, and that is exactly what this is. This is a binary semaphore. It is going to be either 0 or a 1. I'll tell you what it is used for. So mutex is just a name here. It is a semaphore type variable. You can also think of it as a mutex lock, or if you don't feel comfortable having semaphore and mutex together in the same sentence, feel free to give it some other name. Call it lock or whatever you want to call it. So that is a semaphore variable which can take either 0 or 1. We initialize it to 1. I'll tell you why. We have another semaphore called empty which we initialize to n. One last semaphore called full which we initialize to 0. So what are these and why are we using them? What are these? N refers to the array size, the buffer size. This mutex semaphore is like a lock, like the mutex lock. It takes the values 1 or 0. It is going to give you access to the buffer. So if a process has acquired the mutex, right, so if a process has set the mutex to 1, it means that process is accessing the buffer, whether it is the consumer or the producer. So if the producer has set mutex equals 1, it means the producer is putting something on the buffer. So while the producer is putting something, the consumer will not be allowed to take something out. Similarly, and once the producer is done, it will set mutex to 0. Now the consumer can allocate mutex equals 1. It can start reading from the buffer, and while it is reading, your producer will not be allowed to write something. So what are we talking about here? Exactly a mutex lock, right? You have two processes. One of them acquires the lock and is working on the item. The other is not allowed to work until the former finishes. That is what semaphore mutex is for. What about semaphore empty and semaphore full? Very simple. They are initialized to the number of empty and full spots in the buffer respectively. So when you first create the buffer of size n, it has n empty spots and 0 full spots, right, before anyone has started producing, consuming, whatever. So that is how we initialize. So quick recap of the initializations. N is the buffer size. The mutex 1 or 0 binary mutex semaphore is going to dictate who has access to the buffer at any given time. Only one, either the producer or the consumer, can access. The other is not allowed to access while the former is working with the buffer. Empty equals n and full equals 0 represent the number of empty and full spots in the buffer respectively at the beginning. Now the producer process has been structured thus. So while true, as in while it is running, you produce an item, as in you first create whatever you need to be create. You don't put it in the buffer yet, you just produce that item, you get that piece of information ready. Wait on empty. So if you remember the wait and signal functions definitions from semaphore, well and good. If not, this might be a good time to pause here, go back there, look up those definitions in the specific video on them and come back, because we're going to be using these signals here. So the wait function, it's going to claim a resource, of course, but one of the things it does is it decrements the number of instances by 1. If you remember, semaphore S, wait is going to be while true busy wait, then S minus minus. So what is this producer doing? When it waits on an empty spot, it is basically waiting to see if there is an empty spot. Once it sees that there is an empty spot, it is going to decrement that spot by 1, meaning it is using up one empty spot, right? Then wait mutex, so you acquire permission to deal with the buffer, you add the element to the buffer. Signal mutex, you are announcing that you're done with the buffer. Signal full, so your signal function, again if you remember, it increments the number of instances by 1, S plus plus. So the number of filled spots now increasing by 1, right? So what is this producer doing? Again, I will explain the consumer and then we'll come back and look at both side by side. It will make sense. So if you have not completely understood, stay with me for a while. But what the producer is doing is, it will first make sure an item is ready, then go to the buffer, see if there is an empty spot. If there is no empty spot, it will do a busy wait. Once it sees there is at least one empty spot, it is going to decrement the number of empty spots by 1, meaning it is saying there is one less empty spot now because I am going to use it to fill up my information. Then it claims permission to work with the buffer, adds that piece of information to whatever empty spot it claimed. it releases control of the buffer. Signal full, as in it increments the number of full spots by 1. Right. So similarly, we have our consumer process, again while true, while it is executing. Wait full. So it will wait until there is at least one full spot. Once there is a full spot, gain permission to work on the buffer, remove an item, release control of the buffer, signal empty, increment the number of empty spots by 1. So here wait full meaning full is reduced by 1, full is decremented by 1 because the consumer is going to take away something from that full spot. Signal empty meaning the number of empty spots becomes incremented. So it consumes, right? This is the producer consumer process. So what was the bounded buffer problem again? If there are no empty spots, the producer should not produce. If there are no full spots, the producer should not consume. Am I right? Let's go back, check if this is being solved. As in, when I say the producer should not produce, it should not try to put something on the array. That's the point, right? If it produces and if it's able to hold the information with it, that's well and good. So we'll see, here it is producing, but it waits to check if there is an empty spot. Only if there is an empty spot, it is acquiring control of that empty spot. Then it acquires control of the buffer, then only it puts something on the buffer. So until and unless it knows that there is an empty spot, it is not even going to take control of the buffer, let alone putting something on the buffer. Which means if there are no empty spots, your producer will wait until an empty spot is created. Only then it's going to put something on the buffer. So from the producer side, our bounded buffer problem is solved. Let's go to the consumer side. What did the problem say? The problem said if your buffer is empty, your consumer should not consume, right? Again, if you see, it is waiting to see if there is at least one full spot. Only once it knows you have at least one full spot, it is claiming that filled spot, it is going taking control over the buffer and consuming. When there are no full spots, it is going to be stuck in busy wait. It's not going to be able to even try to consume anything at all. So from the consumer side also problem solved. So that was the bounded buffer problem, and that is how semaphores help us solve this problem. So the idea of this is, one, to give you an idea of different kinds of problems that can arise when we are dealing with synchronized processes, and two, to tell you how semaphores are a powerful tool which help you in dealing with these. So in the next segment, we'll be looking at another such problem.